what we have is the lungs are the balloons. And there's a stopper with a hole in it to represent the conducting airways. And so what does this represent? Diaphragm. And the jar represents the thoracic cavity. So if I pull down, I'm increasing the volume in there. Predict what will happen to the balloons.
Collapse.
Yeah, it'll fill actually, because think about it, if I'm pulling down, I'm increasing the volume, decreasing pressure, draw air in. Let's see if that works. They inflate, I push up, they deflate. So if we go like that, it simulates breathing. You can hear the air whooshing through there if you're doing this. So that's kind of why it's a good model for the lungs. Okay, so here they say demonstrate the effects of pneumothorax. That'll just be like if you break the seal and you just kind of like pull it out. Okay, airway resistance. Next topic. All right, so there's this equation here, and there's a figure that goes along with it. It's basically the resistance to airflow in the lungs. F is flow. Airflow is determined by the pressure gradient, delta P, and over R, resistance to airflow. Just like blood flow, we have airflow. And that delta P is people changing from -1, excuse me, I think 0. That whole first part of the lecture where I'm talking about how when you breathe in, you change it to a negative pressure, then it equilibrates. Then you breathe out, change it to a little bit of a positive pressure. So that's the change in pressure there, the mechanics of breathing. The R is largely determined by the diameter of the airways. Now I've been talking about that. Like the trach is 2.5 centimeters, the smallest bronchioles are 0.5 millimeters, right? What we see here, with the first few divisions of the airway, you have an increase in pressure because the airways are getting smaller. Now you are getting more of them, and they start to exponentially increase when you get to like past the 10th airway, and then resistance drops because the numbers are so many, even though the diameter of the individual airways are so much smaller, there's so many that air has much more airways to flow through. You drop the resistance so that when you get down to like the bronchial level and the alveolar level, there is no resistance to airflow. Okay. So the thing about the physiology is, where do we control airflow? At the bronchioles. The autonomic nervous system can control the bronchial level because of the smooth muscle. The bronchioles can dilate. I call it bronchodilation or bronchoconstriction. Constriction is a parasympathetic response. The sympathetic response, the fight or flight response, is when they dilate to reduce the resistance to airflow. But there are other things like, you know, sometimes I need my inhaler because of all the allergens in the air. So allergies and other things can cause the bronchioles to spasm. And I'll go over some of that when we get into the spirometry lecture. So the basic idea is the diameter of the airways largely determines resistance to airflow. Now the control of breathing, there are some neuronal controls in your medulla, and those centers in the brainstem, they're trying to maintain oxygen and CO2 levels. But of those two blood gases, it's really CO2 that's tightly regulated. In hypercapnia, you have too much CO2 in the blood. and the breathing rate increases to get rid of it. In hypocapnia, there's too little, and you decrease the breathing rate in response to let it accumulate. So, hypercapnia, you have an increase in the partial pressure of CO2 in arterial blood. You want to lower it. That's the imbalance. It's the opposite in hypocapnia. Partial pressure of CO2 decreases too much in arterial blood, and you want to raise it. This kind of shows it. You have chemoreceptors. They're kind of in the same place as the baroreceptors. You have central ones in the medulla, you have peripheral ones in the carotid and the aortic bodies. Anyways, both of those, say for example, if the imbalance is too much CO2 in the blood, it's accumulating. Okay? So that increases the partial pressure, decreases the pH. CO2 acidifies the blood. Give you a preview for Monday, this equation here. CO2, when you combine it with water, forms carbonic acid, H2CO3. That's a weak acid, which means it can partially dissociate into bicarbonate. H2, bicarbonate carries a negative charge, plus a hydrogen ion. That acidifies the blood. So that's why we're concerned with tightly regulating CO2. The normal partial pressure of CO2 in arterial blood should be partial pressure of about 40 millimeters of mercury. In this example, say for example, it gets too high. Maybe it gets up to 45. That's too high. It should be 40. Okay? Those afferent impulses will pick up on the elevated levels of CO2, and the efferent impulses will make you breathe more. Okay, basically that's what that's saying. Increase RR. Respiratory rate is always, well, usually breaths per minute. And basically, when you increase the respiratory rate, you help return the partial pressure of CO2 to about 40. Okay, so it's the opposite case in hypocapnia. Let's kind of look at this next slide here. I kind of summarize the results here. What we just talked about is hypocapnia if PCO2, partial pressure, carbon dioxide gets too high, you lower the pH. In the brain, that's very dangerous because in the blood-brain barrier, no proteins can buffer the change in pH, so you can get acidosis in the brain. So it induces ventilation. When PCO2 reaches 45, you double the ventilation rate. In hypocapnia, what you got to know is carbon dioxide is a vasodilator in the brain. So when it drops, you faint because things vasoconstrict. You kind of pass out. Now when you pass out, you stop breathing, right? That allows the CO2 to accumulate and you wake up, okay? If you see someone kind of unstable, well, don't let them faint. Just sit them down, relax them. Maybe they can rebreathe their own air in a paper bag instead of fainting, right? Again, teaching an anatomy class when I bring out cadavers, there's been 2 times where I've seen students just drop to the floor. And one was a girl, one was a guy. So it's not gender related. You see a cadaver, it's early in the morning, you haven't eaten very much, and I'm focused, and you just hear a thud. You're like, uh-oh. One time, the guy caught the girl. It's like, you know, that's preferable, right? But the guy just fell dead. So it can happen. And you just kind of let the CO2 accumulate and you come to, hopefully. The important thing is that you don't hit your head on the way down. All right, so the regulation of CO2 is tightly regulated, not so much O2. You would think O2 is so vital to life that it would be more important to be tightly regulated by the body, but it isn't, because there's so much that's already in circulation that's bound to hemoglobin that's not really a concern. Okay? So you need to see a big drop in O2, partial pressure of O2 before you see an increase in ventilation, because most of it is bound to hemoglobin anyways. Even in deoxygenated blood, you still have 75% of your O2 attached. 75. So you have a huge reservoir. The body doesn't have to as tightly regulate O2 as it does CO2, is the point there. Another concept about breathing is the idea of anatomical or anatomic dead space, which is kind of a misnomer. There's nothing dead. This is just referring to that part of the airways, the conducting airways where you don't have gas exchange. Okay. Anatomic dead space. It's the air just sitting in the conducting airways that's not available for gas exchange. So if I draw my respiratory system, like my little flask, you have air that reaches the alveolar spaces. Air that reaches here. That's available for gas exchange, but the air that's sitting in here is not available for gas exchange. There's no alveolar spaces. So that would be the dead space. Right there in the neck. So every time you take a breath of fresh air, say on average each breath is about 500 ml fresh air that enters. Not all of that 500 reaches the alveolar space here. Maybe about 350 of the 500 will reach the alveolar spaces and is available for gas exchange. Maybe about 150 sits in the dead space. So to calculate the correct ventilation rate, we really wanted to talk about the alveolar ventilation rate. The AVR is considered, well, there's kind of the kinesiology symbol for it. I don't really use it very much. VA with the dot over it. You calculate AVR by subtracting out dead space volume. If we reduce the ventilation below that of dead space volume, then there's no fresh air. There's no alveolar ventilation at all. So for example, let's say you have a big long snorkeling tube that's a volume of 350. And the dead space is already 150. And if tidal volume is 500, well, then there's no, theoretically there is alveolar ventilation. Theoretically there is alveolar ventilation, even though ventilation rates are not. There should be no alveolar ventilation. Consequently, a swimmer should suffocate. So what I'm trying to say here is, I didn't say it correctly. If you're breathing 500, but all of it goes to dead space, you're not bringing any fresh air to the lungs, and you will suffocate. For example, better example, you ever hear of crazy party stunt? Try to sit at the bottom of the pool and breathe through a garden hose. You ever heard of that one? Well, you would suffocate, right? Think about it. That garden hose is really long. So what are you really breathing? You're just breathing your expired air. That oxygen is going to run out really fast. You will suffocate. Okay. But if you're too drunk to care, that's how people die. So, dead space. So, let's subtract it out. Sitting down like you guys are, just normal quiet breathing. Let's assume a normal tidal volume of 500, okay, and dead space volume about 150, and a normal respiratory rate of 15 breaths per minute. If you calculated it out, you'd get that. So let me kind of put the calculations up here. Let's subtract out the dead space volume just from the get-go, calculating ABL. So we got our top line, 500 mLs. Okay, that's your normal tidal volume. So this is the amount of air you're breathing in per breath. So the tidal volume, TV, is tidal volume, not television. Air per breath. So think of it as per breath. But the dead space that you have to occupy per breath is 150. That's the dead space. So subtract it. So that gives you 350 ml per breath. That's the fresh air that reaches the alveolar spaces. That's what you want to use in conjunction with respiratory rate, RR. Okay. So let's see here. Okay, so multiply that by 15 breaths per minute until the breaths cancel out. So it's 350 times 15. Well, I'm sure it calculates out to what I got there. I'll just be sure. $52.50 mils per minute. So that's the fresh air that's reaching the alveolar spaces. By comparison, you can see why shallow rapid breaths don't help you as much, because most of the air ventilated is just sitting in the dead space. So you're ventilating less. If you take slow, deeper breaths, you can see the efficiency increases quite a bit. That's why that works. You're bringing more fresh air to the alveolar spaces. So some questions for you. Let's, using kind of that kind of information, let's solve the top one, and then I'll let you do the bottom one. The top one is Sarah's normal alveolar ventilation rate during mild exercise. It's 6 liters a minute. Okay. Well, at the beach on a warm summer day, she goes for a jog on the beach. What would her respiratory rate have to be for her to maintain an AVR of 6 liters per minute while jogging? And you assume, well, we've been assuming, tidal volume 500, dead space 150. Let's figure that one out. First, let's figure out what are they asking for. We have to dig it out of there. It's asking for what would her respiratory rate be? Her breathing rate. What's her RR? That's what the problem was. What does it give you? Well, it tells you her AVR. AVR is 6 liters per minute. Okay. What else does it give you? It tells you tidal volume and dead space. Tidal volume is 500 ml, dead space. The volume is 150. And I believe that's it. It's asking you for RR. Okay, well, so what you got, what we know is that if you multiply the respiratory rate by the amount of air reaching the dead space, that'll give you that. So let's set this up. Okay, something times something equals 6.0 liters per minute. Let's first figure out the fresh air that reaches the alveolar spaces per breath. That's going to be 350. That's how much reaches per breath. And since it looks like we're using units of liters, let's convert milliliters to liters. I'll just put a decimal point there. So 0.350 liters. That's how much is reaching there. Okay, so it's asking for respiratory rate. So how many breaths per minute? I'll put X, because unknown X. We don't know how many breaths per minute. Multiplied by 0.350 liters per breath. Will give us that. So if you do the math, okay, let's just divide by this. On both sides. So that cancels out. That cancels out. And okay, let me continue over here. So what we're left with is X numbers of breaths per minute equals this divided by that. So I'm just going to multiply and flip it. 6.0 liters per minute times multiply by 350. Okay, so you just solve that. The liters are going to cancel out. So you divide 6 by 0.35. Yeah. So I get 17.14 breaths per minute. That's our unknown RR. Okay? Any questions on that math? You have to be good at math. You want to go into sciences. All right, well, I did that one. Let's look at the bottom one. It's the same thinking. The only difference is, instead of jogging, she's snorkeling. Everything's the same, except now you got additional dead space of 50. So you just have to subtract out more dead space, and I'll leave that to you. Okay. What I'm going to do now is I'm going to shift gears. I actually want to cover the rest of the cardiorespiratory slides in preparation for that quiz, which I said will be histology quiz, which will be on proctoria. So we're going through these slides.